Welcome everyone to a new episode of Embedded in a Nutshell. In today's video, we will talk about the asynchronous serial communication protocol. In particular, we will introduce you to the UART interface. And after this short tutorial, you will be able to tell if an asynchronous serial interface is the right choice for your specific problem, understand the actual transmission flow, read and write data over UART, and debug faulty UART communications. Asynchronous serial interfaces are pretty common even nowadays. These are often named UART, which stands for Universal Asynchronous Receiver and Transmitter. These interfaces actually date back to the very beginning of digital communication. Even the Morse code could be seen as some kind of asynchronous serial interface. One of its major advantages over other communication interfaces is its simplicity and the possibility to bit-bang the transmission. Due to its asynchronous nature, only a single wire, in addition to ground, is mandatory to send data from one system to another. Bidirectional communication requires two wires, RX and TX, which need to be crosswise connected. UART is typically a point-to-point communication interface. As UART modules communicate asynchronously, it is typically required to configure the two communication partners the exact same way. And the most important settings are the speed of communication, often expressed in baud rate, the number of data bits, so typically 5, 6, 7, or 8, the type of parity, and the number of stop bits. To explain your UART, we need nothing more than this hardware setup shown here. An ASCII 328P on an Arduino Uno board connected over USB to this personal computer here. You may wonder why there are no UART modules in the setup, right? But indeed there are. And that's because this Arduino here, it has a secret. Actually, it's not much of a secret as the schematics of the board are open source. Nevertheless, you can see there is a second chip on this board here. That's the ASCII 16U2, and that's because this 328P here doesn't actually has a direct USB interface, but it has a UART interface. And hence, this second microcontroller here, which has a USB interface, is used as a UART to USB bridge. The nice thing about USB, though, is that devices can act as different class types, such as a mass storage device like a USB stick, or a human interface device like a mouse. It can also act as a so-called communication device class, or short CDC, basically simulating an old RS-232 COM port. Okay, here we are right now in the Arduino IDE. To enable serial communication to the computer, we simply need to set the configuration that we wish to have. Remember, the communication configuration consists of the speed, the type of parity, and the number of stop bits. This is done in Arduino simply by calling the function serial_begin with the corresponding setup. Let's use a pretty common baud rate of 9600 and 8 bits of data, an even parity, and 1 stop bit. This can be set using the function parameters 9600, of course, and the define serial8E1. Remember, 8 bits, even parity, and 1 stop bit. Similarly, other settings could be defined here. Now we can start using the serial object and send data over the lines. I typically indicate, for example, the end of the setup in Arduino with a short message, such as setup done, using a simple serial print line statement, as shown here. However, we can send arbitrary bytes over serial. Let's, for example, send the value 42 each 100 milliseconds. If we now upload this onto the Arduino board and open the serial monitor, we see the setup done. That's perfect. But now we don't see 42 actually each 100 milliseconds, we rather see a star. That's weird, right? And that's also not a bug, and we did not do anything wrong actually. The serial monitor here interprets the data as being ASCII encoded. And if we take a look at the ASCII table, the character for the value 42 is actually this star. This means we must know how to interpret the data that is sent to us. Is it ASCII? Is it binary? Does it refer to some protocol? Etc., etc. But now let's hook up our oscilloscope and see what is actually going on exactly on these wires here. We connect it to the TX pin of this Arduino here, which is also connected to the USB serial bridge. And just by looking at the line here on the oscilloscope, we can already see that the default value of the wires is high. So logical 1. This actually dates back to old telecommunication, where this is used as a check to see if the line is broken or not. If we now set the trigger to a falling edge of the TX line, so channel 1 here, we see the transmission of the value 42. I sketched this transmission for you on the slide so we can take a closer look at it. The transmission starts with the start bit. This is the TX line going low for a certain amount of time. And this time is the inverse of the baud rate. So for 9600, this should be around 104 microseconds. But you can see that the line here is actually low for around 200 microseconds. And that's because the additional 100 microseconds is actually the first bit of the data being sent to us. Now you know why it's so important to set the correct configuration on the transmitter and on the receiver side. To read the data, we now divide the signal into portions of these 104 microseconds. After the start bit, each portion represents one bit of data being sent. High is a logical 1 and low is a logical 0. The data is sent LSB first, so we can decode this value and indeed can tell it is 42. This 42 is followed by an additional 1. This is the parity bit. As 42 is binary encoded using just 3 ones, and remember, we selected even parity, we need an additional 1 to make the number of bits a total of 4 and therewith even. This simple parity bit can be used to check the data for corruption. If we assume that even and odd bytes are sent with a 50% probability, you get a 50% chance of recognizing a faulty communication. After the parity, a stop bit is sent, and that's the final one on the right side here. We configured it to be the same length as all the other bits in the Arduino code. So if we would send 2 bytes of data without a delay in between, the line will be held high at the end for at least 1 bit. Perfect, we have successfully decoded a UART transmission. So let's summarize. In order to read 1 byte of data, the receiver needs to know the exact configuration of the communication, the speed, the number of bits, which parity, and the number of stop bits. He needs to wait for the start bit and then sample the bits one after the other. And the time between 2 bits is actually the inverse of the baud rate. The simplicity of this protocol is what makes it so commonly used even in today's systems. However, the achievable data rate is typically not that high if no hardware flow control is used. Still, you can use UART connections without flow control up to multiple megabauds per second. Such speeds can help you realize some pretty awesome and responsive projects, such as this Emulite here, for example. Okay, that's it for this short UART tutorial. If you have further questions, write them down in the comment section below. If you liked this tutorial, give us a brief thumbs up, and if you don't want to miss an upcoming one, subscribe to the channel and ring the bell.